Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax, and on with the show.
Go ahead.
All right, everyone, if I could have your attention. Yeah. Great. Okay, our presentation this evening is, the title of the presentation is Putting Numbers to Bed: Quantitative Risk Assessments. Our presenter, his name is Dave Russell, PE, and he is principal with the Global Environmental Operations. So, without further ado, let's give Dave a big round of applause.
This is going to be kind of free form. If you have questions, I'll take them. Just hold up your hand and I'll recognize you as you go.
Take a microphone.
All right. What is quantitative risk assessment? Everything we do has some degree of risk. Investment, savings, driving, walking, exercise, you name it. QRA is a formal and systematic approach to estimating the likelihood of consequences of hazardous events and expressing the results quantitatively as risk to people, the environment, or your business. It also assesses the robustness and validity of quantitative results by identifying critical assumptions and risk-driving elements. Need me to be louder?
Please.
Okay. All right. QRA is a first cousin to preventive maintenance. PM is figuring out when it's going to fail and changing things out. QA just says what's the likelihood and what are the consequences when it does fail. A good preventive maintenance plan can reduce the likelihood of some of the failures that will be addressed in the QRA because PM focuses on how often the equipment fails and how soon we need to fix it before it does fail. So QRA seeks to measure the frequency of failures and the consequences. Many of you are familiar with the concept of a black swan. Anybody here not? A rare event that's outside the normal range of what we call statistical probability. It's a high impact, low frequency event. Here's, for example, many of our statistical distributions are based on normal student's T, but nature doesn't know anything about a normal student's T event. Nature is much more familiar with a highly improbable black swan event. Tornadoes.
Would you call a fire in LA a black swan event?
It could be, yeah. Under the right definitions, yes. Definitely. Yeah.
If you pose a question, use a mic so it gets recorded.
Oh.
Okay. QRA is widely used in nuclear industry to predict component life, but there's almost no database in the chemical industry or many other industries. This is how you normally express risk. You have, down here, you have almost certain, likely, moderate, unlikely, rare, significant, minor, significant, major, severe. Red, high impact, lower probability. And then this is the stuff that's easy to do. It's the cheap and easy stuff. All right, another way of expressing this that's sure to get management's attention is you put dollar signs on it. And across the top, those are powers of millions of dollars per incident. So you have, the first one might be 100 million to a million. And their frequency, extremely unlikely, and this is in terms of per year. So you might be 10 to the minus sixth down to minor, which could be a frequency of 1 per year, or 1 per month, or something more frequent. Another way you can express this, same sort of concept. You put log scale on one axis, actually on both axes, and the value of F from high to low, value of N from high to low. The red is, again, the highest value, most extreme consequences, and some of the lowest risk, we hope. Probabilities, extremely unlikely, 10 to the minus sixth per year, down to a probable of 1 year, might be an 8 or a 9 on this scale. All right, how did we get here? Well, in 1970, OSHA issued process hazard analysis and process management standards. They were kind of obeyed and kind of ignored in some ways. But then in 76, July of 76, Sevesto, Italy. Sevesto is a chemical plant. And a runaway reaction involving trichlorophenol formed 2,3,7,8 trichlorobenzo P-dioxin, or TCDD, which is one of the most hazardous compounds on the planet. Extreme toxicity over 6 hectares. 640 people got chloracne, and hospitalized 19 children, but the cleanup took 5 years. And they had to put the stuff in a vault that's good for a couple of thousand years. All right, then the granddaddy. December 2 and 3, 1984 was Bhopal. Have you heard of Bhopal, most of you? Look at the numbers. A release of methyl isocyanate at night killed 2,260 people and injured 558,125 people. 500,000 people, over 500,000 people. Most of the injuries go to mucous membranes. If you breathe in methyl isocyanate, it reacts with the water in your lungs and causes them to bleed, and you wind up drowning in your own blood. It also goes to your eyes, any mucous membranes and water. So, as a result of the Bhopal release, the chairman of the board of the Union Carbide Corporation, which was at that time was one of the major leading chemical corporations, was indicted, and a arrest warrant was issued by the government of India for manslaughter. Think of that. All right, in 1996, DOE issued the Handbook of Chemical Process Analyses, which was updated in 2004. All government contracts involving chemical manufacturing have to follow that handbook. June 24th, 1982, European Parliament issued the Sevesto Directive, based on the Sevesto incident. Directive later modified and expanded in 96, and again in 2012. And then on December 11th, 2005, the Hertford Oil Terminal in the UK, Buncefield, exploded. It was so big that caused you could measure that as a 2.4 earthquake value. It was that big an event. So, all right, we know that they're hazardous. Now, what do we do about them? Well, between 2004 and 2008, the EU issued a series of books that are freely available on the internet. They're called the colored books. And there's 5 or 6 of them. First one is the guidelines for risk assessment, how to prepare a risk assessment. Then there's the green book, and that's the method for determination of possible damage to people and objects from release of a hazardous material. It's also known as CPR 16. There's the purple book, that's the guide for quantitative risk assessment. Then the orange book, management of risk concept and principles. Red book, method for determining and processing probabilities. That's where you get into really the damage. They have all the formulas and everything else you need. And that and the yellow book, calculation of physical effects due to release of hazardous materials, liquids and gases. Yeah?
Who did you say put these out and published them?
It's available on the internet. You have to look around because if you just type in the word colored books, you're going to wind up with colored comic books, colored. But if you type in colored books for risk assessment, there's a couple of sites over in England, and basically it was the government of the UK and the Dutch, because they've been dealing with these sorts of issues for years. Government of Singapore came up with, in response to some of this, have a comprehensive guide and requirements for preparation of a QRA. Any new facility going up in Singapore has to provide a QRA and must include total and partial loss of containment for tanks and pipelines, boiling liquid, expanding vapor explosions, operational process errors such as mischarging reactors and overfilling of tanks, bulk transport and pipeline incidents, and alarm failures which lead to incidents. The requirements also include potential for casualties and loss of life from these incidents. So it's not only how frequently, it's how bad. How many people are going to die, how many people are going to be injured. And this is a public document. All right, items that need to be addressed in preparing a Singapore QRA include pool fires, jet fires, flash fires, vapor cloud explosions, pressure vessel failures, runaway reactions, failures of firewalls and failures of blast walls, and toxic chemical and vapor releases. These are all expressed graphically in the event tree that I'm going to show you in just a second. This next slide is it's compact because it's a lot of information, but bear with me because I go through it in parts. All right. First thing is hazard identification. So what's the hazard? All right. Then you have to generate a scenario. And it may not be one scenario, it may be several scenarios. The tank is going to fail, it's going to blow up, it's going to take another tank next to it with it, or it's going to cause a massive fire, which may lead to an explosion or something else. These are all potential scenarios. All right, then you prepare an event tree. An event tree and the frequency analysis. So we'll come to that in a minute. Then you do consequence modeling. And for that, you're doing modeling for injury, fatality, and cumulative escalation. So Then you start looking at what's it going to cost. And then you put together your criteria. What are the criteria you're judging this thing against? And finally, the last thing you look at is how you're going to fix it. How are you going to prevent this? You know how bad, at this point, you've got an idea of how bad things are. But the question is, what are the guidelines? What are you going to use to prevent some of this stuff from being as bad as it might be? This is the full QRA list from Singapore. And like I say, it's rather extensive. I've cut this down in sizes so it's a little more readable. There's one at the very left is the top event.
Dave's question.
Yeah.
How do you develop the scenarios?
Just talk, it just records.
Yeah, when you talk about scenarios, there's a lot of different ways things can happen. So does it, you have a group of people sit around and brainstorm scenarios?
That's entirely up to you. That area is not really defined. In other words, I can imagine scenarios that are frightening. Somebody else may say, minor. But the point is, when you get down to evaluating the release, then you have to look at the potential for injury and damage. And then you have to go back and say, okay, now, is this scenario reasonable?
So in the event of, say, an overflow of a tank,
Yeah.
so you would have a sequence of failure of devices, and if they're common devices, there's a mean time between failures for each device. So the level sensor, the pump flow meter, the release valve, and so forth. And it's just a multiplying of these factors. But there are many things in the mechanical world that don't have that, or the structural world that don't have that. How would you put factors on Surfside, Florida, where the building collapsed?
Experience. And there is a database, and I'll get to that. But I wanted to kind of go through some of this. So on the far left, we have the event, which is the top level event. Then you have your source terms, immediate ignition, delayed ignition, flame front, inhalation, additional modifiers, and the final outcome. Now this is 1/4 of the QRA. Same columns. And the lower portion. The point is, it's comprehensive. It's got to be comprehensive. If you all remember Deepwater Horizons?
Yes.
All right, the failure fault tree on that was something like 300 lines. They went through everything that they could find from the fault tree. It was just amazing. It was up at one point. I think it's been taken down now, but it was very comprehensive. They went through that with a fine-tooth comb, and even down to, okay, this valve failed, this one didn't, so on and so forth, and the sequencing.
They did that before the event or after?
Afterwards, obviously, because the facility wound up at the bottom of the Gulf.
That's what I asked.
Yeah.
So it wasn't a proactive
No.
assessment?
It would have been nice if it had been.
Repeat the question for the report.
Go ahead, repeat the question.
Was that done, the fault tree done before?
No, the fault tree was not done before. The fault tree was done afterward. The facility is now down at in the bottom of the Gulf somewhere.
So it was not a proactive?
No. If it had been proactive, there's no guarantee. It might not have happened, but at least somebody might have been more aware of the possibility. All right, for a large ammonia tank, Here's a typical QRA. And we're looking at storage, failure, gas release, liquid release, various things. And the other thing you have to realize is that ammonium is potentially flammable. So that's a possibility as well. It's a gas that's lighter than air, but yet at the same time, it is flammable. It's also 500 to 600 ppm of ammonia can blind you. And one of the things that I learned way back when I was in the chemical industry is that we were concerned about ammonia releases, because if you got 500 to 600 ppm of ammonia anywhere near your eyes, they'd tear up and you couldn't see, and you were choking. Think of that if you're driving a truck. It's a very hazardous sort of situation. Now, talking about that fault tree you just saw, here's a description. It's easier to read. So you have a catastrophic loss of containment. Several types of possibilities: hole in the tank, overfilling, transfer failure, transport failure. Source, gas and vapor, aerosols. Unobstructed or obstructed, you have the possibility of a pool of ammonia that's evaporating, flashing, and plume buoyancy. So it's something that you have to consider. Now, ammonia is lighter than air, but there are other gases that we deal with a whole lot that are heavier than air. Is it water reactive? What's the stability class? In other words, how much mixing do you get, vertical mixing, as the air moves across the land? Do you have isolation or detection equipment? Is the neighborhood sensitive? Do you have receptors out there, or are the receptors people? Are there third parties that can be helpful or hindrance? All these are questions that need to be really looked at in a good QRA. One other way of looking at hazards is what we call bow tie analyses. Your main event, such as your failure, on your left there, you have the causes, your threats, and modifiers and sub-threats. Then you have your main event. And on the right, you have your recovery. What are your prevention techniques? What are the things that are you going to do? Shelter in place? Are you going to do shutdown going to do evacuations? Can you do evacuations in time? Can you set up water sprays? These are all questions that need to be looked at when you're looking at. Now the Ishikawa or fishbone analysis is basically a half of the bow tie analysis. So you'd put two together, pointing in opposite directions, you'd have the same thing as a bow tie analysis. It's just a different way of looking at things. All right, there are programs to determine your consequences. So you develop your scenario. Okay, we have a leak. What's the leak? Well, there are programs by EPA and other people that will tell you what the consequences of your leak could be. And these consequences can be calculated with some precision through air modeling. And I've listed the air models and the documentation. And then there's a page on Blevies and fireball dynamics. And then Cameo is a marvelous little program by EPA. It has a whole bunch of these things all put together, and I'll touch on that in a minute. All right. There's a possibility here. There are water quality programs will look at water releases to water. WASP is a water quality model for multiple pollutants and can consider eutrophication effects. There are various consultants that have programs for modeling heat flux from fireballs. Commercially available programs are available for calculation of that information. For toxic probates, and this means basically we're talking about deaths, use the Green Book to evaluate. And for Singapore, they see 3%, 10%, and 50% fatalities, and they want to know what those are and where they are. And then for air modeling, consider high stability, nighttime evaluation, windrows, use high humidity. The thing is that a lot of these events generate air releases. It's the air releases that impact the people that cause a lot of the problems. There are commercial companies such as DNV, FAST, TNO Effects, Circadams, and so on. And there's one from AICHE, which is RAST and CHEF. RAST is an Excel program. I don't think too much of it. CHEF is available and is consequence modeling, but it's $8,000 a year for subscription. So it's kind of expensive. All right, now I said there was failure data available from people in the UK. The UK HSE is the Health Safety Executive. They're the OSHA of the UK. And they talk about HSE events for LPG pressure vessels, chlorine, and other vessels. These are the approximate frequencies that they expect in terms of incidents per year. We're not talking about very large probabilities, but the consequences are great. And this goes back to my earlier point about this black swan model. They aren't frequent, but when they do occur, watch out. And this is for various size holes. And for example, on a chlorine vessel, 4 times 10 to the minus 6th incidents per year per meter of pipeline. Yeah. Rates for storage tanks. BEVI is the Dutch version. Instantaneous release of entire contents. 5 times 10 to the minus 7, I think that is 7, yes. Continuous release, about the same. Continuous release from a 10 millimeter diameter hole, 10 to the minus 5th. Failure rate for pressurized above ground pipe work, again. And you'll have access to all these numbers. So I'm not going to go through and read the whole bloody thing. But when we talk about things like pipelines, rupture in the pipeline, catastrophic failure, 10 to the minus 6th. And so, and then some summarized results. Dominant causes of loss of containment failures from the Dutch study were incorrect materials, inadequate control of process streams, making safe items in the plant prior to maintenance, errors in assembly of components, for example, loose connections, failure to recover process deviations, failure operating containment with direct links to the atmosphere. In other words, somebody forgot to close the valve, and they started up the process. UK study, Most failures occurred under normal operations, startup maintenance operations. Approximately 52% of the accidents occurred despite the fact that the system had at least one safety barrier. That safety barrier could have been a fail-safe, a pressure relief valve, it could have been electronic component or whatever. But 65% of the failures were due to bypass, 17% due to leakage and catastrophic failures, 16% in the accident study. In the study, 20 of the incidents and the quantity of material was above 1 ton. In 22 accidents, there were injuries. There were 46 casualties. 17 were hospitalized with burns, chemical burns or poisoning, and approximately a third of the people injured were contractors. So we're talking about an active, dynamic situation. All right, the effective safety management failures. The various categories across the bottom: dispersion, uncontrolled dispersion, controlled dispersion, fire, jet fire, pod fire, explosion, vapor cloud, direct dust explosion, explosive decompression, other, and there are some that were not reviewed. And I'm just, like I said, I'm just highlighting a few of these. The studies are available. When we looked at 56 accidents in the MARS, which is the major accident reporting system in the UK and in the EU, 27% of those were general classification chemicals manufacturers. Petrochemical refinery was due 16. Pesticides, pharmaceuticals, and others is 6, and the rest are smaller, fortunately. Now I'm going to bring in, this is going to kind of bring it home. We're going to look at 2 scenarios. One scenario is out in California, in the town of, south of, it's a town near Lathrop. And it's involving the release from 2 old refrigerated liquid ammonia tanks. These are massive tanks. And the other release is from Georgia, and it's a tank car release. I'll go through these. Here's Stockton. Stockton is on a river. The river is navigable to open waters through the San Francisco Bay, and the port is right just north of that yellow circle, one of the unloading areas for ships. They bring in massive shiploads of refrigerated liquid ammonia and pump them into these massive tanks, 150-foot diameter liquid ammonia tanks at minus.
Where does the ammonia come from?
It is probably Russian ammonia. It was at one time, and may still be. There was a deal worked out by Arm & Hammer 40, 50 years ago where he was selling phosphate to the Russians in exchange for their ammonia, and he basically ruined the ammonia market for local U.S. producers because he was able to bring the stuff in at bargain basement prices. So anyhow, the 2 tanks, you can see them there, there's little dots almost right in the center. Here's a larger area of the tank farm. They have trucks that drive up along just north of toward the top, under the between the railroad and the tank farm. Now the tanks are protected by dikes, but the dikes are 5 or 6 feet high, and one of the tanks releasing would pretty well fill that dike, because you're talking a couple of 100 feet in each direction. So you've got a large surface area of volatile ammonia. Here's the effects. I include this just for reference sake, to talk about the chemical data and so on and so forth, and to introduce the AEGL. AEGL is Acute Exposure Guidelines for Air Toxics. And they have 3 classes, 1, 2, and 3. 60 minute is 30 ppm. 60 minute at AEGL2, 160 ppm. And the AEGL3 is 1100 ppm. IDLH is 300 ppm. IDLH is immediately dangerous to life and health. All right, when you look at this and do some modeling with this, here's what you get. The red area there is the danger zone. This area here is the 300 ppm line. These are lesser concentrations. This is the lowest concentration, but it stretches almost 6 miles. So if you're in that area and you don't get out, you're done. But that's life in the big city. Here's the threat zone without the graphics involved. So this is all from, it's in the public database. You could reproduce these figures exactly.
Dave, is that just one tank going off?
That is just one tank. One tank, the assumption is that one tank would put a layer inside the diked area and it would evaporate from there.
So
Yeah.
that yellow zone that went 6 miles, the
yellow zone that extended 6 miles,
that's considering a prevailing wind at the time?
Yeah, yeah, it is. The previous slide, I introduced the, I'm sorry. I had introduced the previous slide. There's the windrows in the upper right.
Okay.
And that shows the prevailing wind. This is the approximate direction. So any release is going to go in that overall direction. And you can plot this stuff out with some of the EPA programs. 4.2 miles. I'm sorry, I was wrong. Not 6, just 4.2. All right, when we get to something a little bit closer to home, I want to talk about transportation-related incidents, because they are of concern. And again, the Dutch and the English have good databases. And this is the frequency Dutch data on transportation-related incidents, and the frequency of incidents per 100 meters of track. Not kilometers, meters. Now, understand that we're dealing with the Dutch, and that's a much smaller community, but they do have a chemical industry. So, and you can see that propane and chlorine are also listed. So you get some sort of idea as to what the death toll might be from some of those releases. When you talk about things like East Palestine, that was the chemical incident we had, what, 2 years ago? The Dutch data on hazardous chemicals from rail transport, they're not shy about listing fatalities. The green zone, the area inside the green zone, you're pretty well cooked. if there's an hazardous material incident in that area. So you've got some choices. All right. Now, by comparison, U.S. data for hazardous rail shipments, 21.2% of all shipments are flammable gases. 14% of shipments are corrosive materials. 48% are flammable. And 2.4 are non-flammable gases and poisonous materials. And they have some statistics regarding hazmat non-accident release rates and then accident release rates. Accident release rates are much lower. But don't forget, we have a huge volume. This is the entire U.S. fleet. And how many thousands of shipments of tank cars are available out there? East Palestine was just one. The next scenario is a chlorine release from a rail siding closer to home. The scenario is very simple. What would happen? They have a rail yard over in Austell. I think most of you, everybody here knows what it is or have seen it at one point or another. What would happen if they had either a 3-inch hole or a bottom valve, a 3-inch diameter bottom valve, in a tank car full of chlorine? Break off. It's not pretty. Here's the site data. Red zone is 5.3 miles at 10 ppm. Now, chlorine is a heavy gas, so it'll stay close to the ground. Ammonia, by comparison, will diffuse upwards. But under reasonable or high stability conditions, you might be out at 5.3 miles for your red zone. Your orange zone, greater than 6 miles, and your yellow zone, greater than 6 miles at over a half ppm. At that point, you're getting irritating, and you're going to notice it. It's kind of comparable to what happened in Atlanta from Conyers. There it is. You can see where the rail yard is. The rail yard is right here. And this is the prevailing wind direction. But the thing you have to look at is that this is a wind direction based on the probability of this portion of the windrows. The wind can also go back in the other direction as well. So you've got a larger area that potentially could be affected. All right. Let me bring this back. I believe that there is a greater need for transparency on the part of industry and transportation organizations to educate the public and assess the hazards. Just flat out. One of the reasons that the data on accidents from industrial sites are not readily available is that we all are a litigious society. What's the first thing you see advertised on TV? Lawyers. What is this accident worth to you? Make sure you get your maximum amount of, yeah.
I just want to point out, in case anybody missed it, as of January 1st, lawyer advertisements are no longer allowed on MARTA buses.
Thank you for MARTA. One of the reasons data on accidents from industrial sites are not readily available is that we are a litigious society. And no executive in his right mind would ever want to go up against a jury in a trial and say, yeah, we knew that we had a 1 in 3,000 chance of something going wrong, he'd get crucified. Just simply crucified. So, that's it. Yes, Roger.
So, Fukushima, I guess they had a scenario where the tank would go dry, and their solution was the fire department would show up and spray water. But the reality was whatever caused the tank to go dry also disabled the fire department. So how do you do a risk assessment looking for all those kinds of convolutions?
Basically, you have to go through it piece by piece and find out what's the root cause. Go ahead. You're causing, what you're looking for is root cause analysis. All of these things have some sort of sequence of events, and each event has a certain probability. And you add them, or multiply them, or subtract them, depending upon how you formulate your release model or your accident scenario. In some cases, they are additive. In other cases, they're multiplicative. So in some cases, if event A occurs, event B may cut it off. But if it's an OR situation, you may have event A or event B, either one of them fail, you've got your release.
The chemical industry does these things called HAZOPs, where they sit down for weeks at a time and go through all possible combinations of problems that could happen. And those are all documented and legally required by the government currently. And what I'm wondering is, all this stuff that you're talking about here doesn't sound like much of it's mandated by the government to be done.
It's not.
So none of this is being done on these tanks like this?
Right.
Whereas inside a chemical plant, they've got to go through all of this stuff very carefully and look at all this stuff. And then come
They
up
look
with
at
answers
what's
and
happening
solutions.
inside the plant
Yeah.
and what happens to the reaction, but not what happens outside the plant. Hence, we have Bhopal.
So we have a solution inside the plant, but we don't have a solution of a methodology in place outside.
That's right.
Wow.
Yeah. So,
Doing risk assessments of machinery. And yeah, you come up with mitigations of the hazard. And sometimes they'll, okay, what's going to go wrong, the mitigation. So on a machine, typically you don't have a Fukushima situation. Yeah, if you're having a machine with hazardous material, well, we had Gainesville with liquid nitrogen leak, Vent 2, and then they didn't have good flow control on their piping. Yeah.
yeah, and you can get this, for example, even in wastewater treatment plants. What was it? Right around 2000, EPA came up with a program called RMP2, which was Risk Management Program. And they started looking at releases from ton cylinders of chlorine. A ton cylinder release of chlorine can contaminate an area of around 2 miles in this type of scenario. They got so many complaints from all the municipalities saying, I can't live with this data. You're telling me that the 1 ton cylinder I have, if it leaks, it can cause a 2 mile evacuation? Yeah. So what'd they do? They took the program down.
The point was made earlier, there isn't a government mandate for doing risk assessments of this nature in many situations.
That's right.
Overseas, evidently England, Holland, Singapore have these requirements.
Lots of the EU does.
In Canada, some of the provinces require an independent health and safety review before a machine goes into operation.
Yeah.
And that's not chemical equipment, that's just, if it's a packaging machine, for example.
Yeah.
We do not have proactive.
We're
OSHA
fat, dumb, and
requirements.
happy as far as that goes. We're fat, dumb, and happy until there's a problem, and then you've got East Palestine all over again. Yeah.
This is just very general. But for instance, Roger, you were mentioning European standards versus U.S. standards. I'll just pick a simple one. If you see gasoline tankers on this road all the time. In the U.S., there's no rollover protection on those trailers. Yet in Europe, they're in a steel cage. They're in a cage.
Yeah.
They're light years in certain areas, light years ahead of us in safety.
Let me mention one. Georgia schools, the Facilities Services Group of Georgia schools, whenever there's money being put into a new school or significant modification, they require some type of risk assessment, and they have definite criteria that they want you to go through. And I've done a number of these for Georgia schools, and it's little things like, in some cases, the hazard is very low, so you develop a scenario, and one of the ones over in the Marietta area, I developed a scenario that said, okay, we have a tanker truck traveling alongside the school, and it got T-boned through a car, and that caused a release of gasoline and a BLEVE, which is a boiling vapor expanding liquid explosion. Boiling liquid expanding vapor, sorry. And that creates a big fireball. And that's a radiation hazard. And so we looked at it and said, geez, this is tough. It's a minute, maybe 2 minutes, but anybody in that playground would be impacted, could be impacted severely. Or anybody in the school close to a window could be impacted severely. So what do? I came up with, pardon me for patting myself on the back, a solution that absolutely frosted the local landscaper, because I suggested along the active road that they install 3 lines of evergreen trees. I don't care if the evergreen trees burned up, but I don't want the kids burned up. And that was enough to shield the kids who might be in the playground in the event of this type of occurrence. So, and there are other instances, not the least of which is Austell and the wind direction in Austell, or
I live out that way.
well, and what happens if you have a major incident on 75 or 85, and the wind is blowing in the right direction toward a school? Some of the schools have even put in a master switch so that they can shut down the air conditioning system. That shuts down all the intakes, and then you've got shelter in place for a period until the fire department or whatever can respond and get the kids out. But these are the types of hazards that we deal with, but unfortunately they're not well understood.
One of the places in Georgia that you can get training on ammonia refrigeration and safety is Lanier Tech. They have a relatively new campus, a number of buildings. The building that has the ammonia lab in it, they have multiple sensors, they have all the to code safety features for their ammonia handling. But if they get an ammonia leak in that building, it shuts down the air intakes on all the other buildings on the campus. Doesn't do anything for the Quick Trip gas station up the corner, though.
Right. But, for example, again, let's consider Biolab. There was a fire. What was the cause? Let's look at the root cause. The root cause of the fire was water got on some stored product. Now, there is a CSB, Chemical Safety Bureau, csb.gov, just released safety briefing, a video, on the causes of that type of incident out in Louisiana, where a windstorm came through, took off portions of the roof, and that the rain associated with the hurricane got the product wet and caused a fire. The fire released chlorine. It happens.
You mentioned the Chemical Safety Board. It's a federal agency without enforcement powers, but investigative powers.
It has investigative powers, yes.
They will investigate chemical accidents, and they will release their findings as they make them. They don't wait for 3 years to have a final conclusion.
That's right.
You can subscribe to their email that they send out periodically.
csb.gov. So, further questions, anybody? Okay. Thank you all.
A bit sobering, if nothing else.
Yeah.
Here.
Thank you.
Accept that on behalf of.
I appreciate it.
Really appreciate.
I appreciate it.
taking the time
Okay.
and imparting the knowledge on us. Thank you.
Well, let's see what happens.
See what happens. All right, folks.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at GSPE.org.